It is my pleasure to introduce Adam Cron from Synopsys, who will be talking about power-aware DFT and ATPG. He is the principal engineer at Synopsys, working with customers on DFT and ATPG issues for digital ICs as part of the Hardware Analytics and Test R&D group. He's been with Synopsys for over 23 years. He is also the chair of the IEEE standard 1838, which standardized 3D IC test access, and previously chaired the IEEE standard 1149.4 working group through its release. And he has a degree from Syracuse University. And with that, I turn it over to you, Adam.
Thanks very much. And thanks to everybody who's still on the line. For a second there, while Dave was talking, I looked up and I saw Ken's mic was unmuted, and I thought there was going to be an ATE-CAT fight, but cooler heads prevailed, which is good. So a lot of these slides are going to address things you can do from a DFT standpoint and an ATPG standpoint, ATPG being pattern generation, to reduce power at the time of test, and then we'll move into the correlation part. So these slides kind of begin with power DFT, but then move on to the real title, which was correlation related. So as has been said by Arun, who was really speaking my language earlier, test is very power hungry, so I don't think we have to dwell there too long. I will say that the tools today, from a design standpoint, do understand multiple voltage islands as well, but we're not talking about that today. Putting in logic level shifters and isolation cells, for example. But I will touch a little bit on mission mode power reduction, just because I think it's relevant to the topic we're talking about. So I'm going to start with hardware mitigation techniques and then get to patterns later on. And I'll again start with shift in hardware and get to capture later on. So the first one was actually mentioned earlier, but I'll get into more details on it. It was mentioned by Ken, QGating, which is a technique which blocks the wiggling of the scan data as it goes from the flop into the functional logic. So for example, here we have a big scan chain, and the scan chain is driving some cones of logic in the design. And what this does is basically automatically puts in gating logic, AND gates, OR gates, or whatever, so that while shifting, we don't activate the functional logic. Because when you're shifting, if you don't have a big load, this logic might not wiggle too much, might not have much IR drop there. But if you have a large load and you start wiggling that scan data, all of a sudden you might get a big IR drop, and that could impact the results of the test going forward, and we're trying to kind of avoid that. And so this adds the gating logic, and therefore you don't really care as much. So I will note that you want to use this sparingly, because it also has its other issues like leakage, for example, as well as potential coverage or congestion kinds of issues when you add this. So use it kind of sparingly. There's another collection of mitigations for shifted data, which really involves blocking or changing the data that's coming into the design. So if you have a bunch of scan chains coming in, this compressor, a register, which can be filled by the pattern generator, can be used to block particular sets of data as it comes into the design, maybe making it all zeros or whatever. And this is, again, an automatic thing. It's typically done for compression type logic where you don't have direct access exactly of all your data going into the scan chains. So this would have a shift register and an update cell, and the update holds during the particular shift operation so that you can shift in a new value for the following vector to work with during shift to help block these scan chains that you might be selected. So the benefit here is that you do lower switching activity when you compare ATPG only techniques. So we've added some hardware to zero out some chains, so you do lower switching activity. But the other interesting thing with this is that you also, because hardware is helping lower the switching activity for you, you can focus your other bits on real care bits at the moment. And so you actually lower pattern count too, which I thought is an interesting side effect of this. So you do get something for nothing almost. This can also be used in logic-based kinds of situations. And you might use the pattern counter, or there's other ways to actually drive this. But the idea is the same, that some random data and multiple patterns inside the device during a logic-based function could be used to load those chains with zeros. Again, lowering.
So 2 slides back when you talked about just lowering the number of vectors, I mean, that directly correlates into test time, correct?
Exactly. Exactly. This is rare. When you're trying to address power issues, it's rare that you get something back for your investment. A lot of times, at least from a pattern standpoint, you're going to expend patterns to lower your temperature profile. But in this case, we're adding hardware, and it works out actually very nicely. Other kinds of logic-based mechanisms either are going to hold data to keep constant values shifted into chains so you don't switch during the shift process, or stall the pseudo-random pattern generation function during logic-based to try and, again, hold the values going in. So again, this is a case where you don't really have direct control of the data. You've got an LFSR generating data for you. So you need some way to kind of automatically reduce that switching activity during shift. So another thing you could do is, and this was alluded to as well in an earlier discussion, you can dither your scan clock. So if you have a chip that has multiple shift clocks, you could misalign them so that all the shift edges of all the clocks don't line up. However, that's getting more and more unusual. So you could really do the same thing inside your design. If you have a single shift clock, for example, you could delay those at different times into your, let's say, on-chip clock controller function, which fans out to different blocks of the design. And then again, by that same token, you could misalign capture edges during shift. Same thing could be done today. A lot of folks are using serialization, deserialization in the scan chain. For example, data might come in on the USB at a very high speed, and so you have tons of opportunity to ratchet that clock speed down to something that you're really going to shift at. So you can pick off, for example, I'm showing picking off different phases of the same clock. In this case, taking one clock, multiplying it up, dividing it down. But like I said, for serialization situations, you can do that fairly easily by picking off a phase and feeding that to your shift clock to, again, misalign the shift activity that's going on. Another thing that could be done, again, a little more expensive, and also having extra hardware, is you could shift in different boxes at different times. For example, we could load up the green box with its scan data, and then switch and load up the red box with its scan data while holding the green data. And then you go to launch and capture, and then again, unload the green data, unload the red data. Again, you have to have some hardware in there to make that work, and it is going to cost you in terms of test time because you're doing things serially now. But that's certainly a mechanism to save power during shift. These next couple of slides are an inspiration for another little bit coming up, but I saw these in 2014 during Southwest DFT, and ITC actually was presented by AMD. And when I saw them live at Southwest DFT, I thought, brilliant. This is money, printing money, basically. So here, I'll give you the takeaway. So if we have shift happening and then launch and capture and shift, we're going to focus on the shift. So the idea is that what AMD was seeing was when they started shifting, boom, all of a sudden they saw this 200 millivolt drop, which was causing a yield issue. So this is their real slide that they're showing. I'm just kind of redoing it here so you can see it a little better. So lo and behold, they slowed the shift clock down and they didn't get the big voltage drop. But they also didn't get the yield metrics that they wanted, right? They weren't cranking out parts as fast as they needed to on the back end. Again, this is AMD information. So certainly slowing the clock down gets them their yield back, but it's taking too long. So the idea here is, hey, let's slow it down a little bit, but then speed it up later. And I thought, hey, that's pretty brilliant. And of course, the trick is finding, where do you, what speeds do you use here? What's the slow speed? What's the fast speed? And where do you make your break? So in their case, again, printing money, they did 25 cycles at 62.5 megahertz and did the rest of the 500 cycles at 125 megahertz, saving test time, in fact, and yield at the same time, because they thought they were going to do 100 megahertz to begin with. And that wasn't working at all because 100 megahertz was giving them their yield issue. So they slowed things down, then sped it up, saved time, saved yield. It was, again, pretty brilliant idea. So leveraging that same issue, and again, this is something that Dave was mentioning as well, for logic BIST, you want to start slowly from a shift standpoint and end slowly, slowing down as well, so you don't get this big spike in current need, and therefore a big IR drop, which can't be satisfied, for example, in an automobile with the wimpy wiring and poor power distribution circuitry. But slow down, then start your logic BIST at speed, and then at the end, as Dave was saying, at the end you don't want to jam in a bunch of current as you turn off logic BIST immediately. So slow down gradually so that supplies can react and you don't get issues. So now we're going to go into capture time. So capture happens typically after shift, and a lot of the ATPG methods actually are going to leverage the fact that you've added clock gating into the design. So let's talk a little bit about that. Here we've got a situation where in your RTL, there's some kind of a loop Q to D. The synthesis tools are going to see that, and they're going to put in a clock gating cell for you that saves gates or area, and then it also takes the clock tree and allows you to clamp off or turn off that clock tree earlier in the tree, thus again saving power. So then these are going to be scan flops, and then you're going to go through your insertion process, and at the end the scan enable will be controlled as well so that you can shift. So shifting is very important, obviously, to do scan test. But the clock gating functional sensitization is what's being used during ATPG to mitigate the capture function. So because some of these cones are very large, there's other features you can use to add more DFT only flip-flops to limit the capture. So for example, here's a functional flip-flop with its clock cone, and here's the clock gate that normally would be dropped in. And what this feature does is it drops in a DFT only flop, which also drives the functional pathway. And so now scan or logic BIST can randomly fill this with a 0 and turn off that clock tree easily so that we can, again, stop the switching activity for the entire tree there. This also is supported for other situations, for example, when wrapping is used. If a block is not used during the pattern generation phase for multiple blocks at a time, you can turn off the entire block by some DFT only clock gating. So here we have, for example, multiple groups of designs, and they're being tested several at a time. Again, to mitigate power during test, you can test blocks serially instead of all in parallel. But the blocks that are off, you can use DFT only techniques to turn that block off completely, including its entire clock tree. And then there's a little bit here talking about hardware related to mission mode. So in compression, a lot of times there's an X blocking function, and the X blocking function helps block X's before they go through the XOR tree. because as an X drops through an XOR tree, it blocks a whole lot of other scan chains. So you don't have to worry too much about that. But in mission mode, we can leverage this X blocking function to just stop any wiggling that happens in the functional flip-flops as they go to this XOR tree. So that in mission mode, again, you're shrinking the amount of switching activity that happens at that time. Now, another interesting mission mode, I dropped this slide in late in the game. It's not in the slide of downloadable stuff. But this is just kind of some of the weird stuff that people do for mission mode power mitigation, not DFT mode power mitigation, but I'm putting this in there because it relates to DFT in a way. So the trick is, here we have on the right side, we have a register bank or a lot of flip-flops. And these flip-flops are fed by some combinational code of logic. And the trick here is the inputs to the register bank are compared with the outputs of the register bank through this XOR tree. And then if the data is the same, it turns off the clock gating cell of the clock tree. It's insane. It's a lot of logic, it looks like, to turn off the clock gating cell. But the point is, your clock tree could be around 50% of your power used. And the reason I'm showing it here is because this particular function mode mitigation happens to create a DFT coverage issue. And so there's automation and tools to add, other test points and things like that to solve this coverage issue, because it turns out that if the clock tree does fire or the clock tree doesn't fire, it really doesn't matter because the data is the same. So you need some observation here, and these are tricky faults to detect. The point is that there's lots of other mitigations for power on the functional side that we're not even touching here. So let's go to pattern generation. So pattern generation, and any questions, by the way, for the hardware side of the world?
No, not at the moment, but I mean, okay. Obviously, anything you add to the circuitry just means more stuff you have to test, so.
Sure.
And
Sure. So let's get into the pattern data first, again, starting with shift. Let's just say that during a test at all, a scan-based test, only about 2% of the bits are care bits, which means we have 98% of the bits we can fill with garbage. Well, if you randomly fill, you could get unlucky and do a lot of switching activity during shift. Smarter to do some other kinds of fill so that you get less switching activity during shift. And so there's lots of ATPG techniques that apply to this kind of savings. And you can see the results here without any shift switching ATPG mitigation techniques. You get a bunch of switching typically at the beginning, and then it's tails off into something more manageable. On the other hand, if you can turn on and actively stop the switching activity during the shift operation by just scanning in less changing data shift to shift, then you can get some reasonable switching activity. But like I said, you're paying a penalty. You don't get something for nothing. So typically in these kinds of techniques, you end up with a longer test. But on the other hand, yield is good too, as was mentioned in one of the earlier presentations. So capture, remember I mentioned early on during the insertion phase, clock gating is added. So clock gating is going to be leveraged to help us reduce switching activity during capture. So for a particular test, you might have loaded your flip-flop with a 0, sensitized it with a 1, and then when the clock comes along, you get this capture event, which wiggles a bunch of stuff over here, and again, you get some IR drop. So the idea here is to leverage the clock gating cell to turn off the whole tree after the clock gate, so that not only do you avoid the up to 50% wiggling of the tree in this neighborhood, but you also don't get the switching activity that happens here either. So by that token, you get a lot of reduction. And there's been a correlation. This is very important. We're starting to get into real measurements here, which I'll get to following. But ARM, this is 2007, folks. ARM did some testing, and they showed that flip-flop switching activity did in fact correlate fairly well to power used in a design. This is a Cortex A8 design. And anyway, you can see within 15%, that's not bad in 2007. I would hope things are better. I don't know. But it doesn't matter. There's a correlation between flip-flop switching and power. So the tools can very easily mitigate switching activity by turning off the clocks during capture, or as I mentioned, using the clock controllers as well. On-chip clock controllers can be just not turned off during the capture operation, or we can leverage all those clock gating cells that have been dropped in here and there, and we can again, on a pattern by pattern basis, we can enable a couple of clock gating cells for one pattern, and we can enable some other clock gating cells for another pattern, thus again reducing the switching activity during capture. So all this stuff is all automated in the tools, no issues there. The issue actually is in the user setting these tweaks, and again, now we're getting closer and closer to correlation. So without these mitigations, capture switching activity, this is for a particular design, without these mitigations happens in this neighborhood, 15%, whatever the number is. As I apply a mitigation, as I tell the tools, you know what, stop switching so much during capture, you can see it does a good job. It does stop switching activity during capture. But as I push that value lower and lower and lower, you can see eventually I tell it too much. It gets to a point where the circuit itself can't respond to what the tool is trying to tell it to do. And so you end up with this floor, if you will, of switching activity beyond which you can't get. And in fact, probably to avoid under testing, you probably want it to be in this neighborhood anyway, of the 5% versus the 2.5%. So you got to watch out for that too. Don't want to under test. So now we get to
before you get to correlation, there was a question, controlling the test stimuli leaves the responses uncontrolled. So should the power reduction looks more significant than what would be implied by uncontrolled outputs? I don't know if that question makes a lot of sense. That's from Eric Yan, but worried about if you're turning off clock trees, or you're not putting inputs in, or your outputs just randomly set, and is that going to make your power consumption go higher?
Right. Yeah. So no, this is, in this particular case, this is a case where and for all of the scan-based testing, we're always setting all the data. So there's definitely data in there. So there's no X's, if you will, in that environment. We're just trying to set clock gates to turn off in this particular case. Okay. Or turning off system clocks. Yeah.
Okay.
So now getting to correlation, let's go to pre-tape out first. Again, these slides are presented for a long time, and so this, I keep updating with new things in there. For example, the self-gating that I showed you for the memory arrays. But here's some old data. Prime time PX can tell you with some kind of switching activity how many watts you're using. So you can see, more switching, more power. We know that. So I wanted to look how that really looked in a design. For example, if we have a core here, let's say core A, one instance, and we have the same core A, another instance, but we have power and ground pins, located over in this corner here. What does this look like? If you have a pulse on this clock mesh, then we have some kind of, IR drop profile. But if the same pattern is applied over here, because we're farther away, we get a different profile. So now all of a sudden, it's not just flip-flop switching necessarily. So that's become a kind of a worse correlator, or not the best collection of data. We need to actually know about exact current profiles of the cells and even the parametrics of the mesh itself to draw some conclusions, or to drive the tools to do the right thing to avoid IR drop in different places. So here I'm going to show you a quick example. where I took some patterns, I put them into primetime PX, I got simulated them to get the VCD and then put the VCD in primetime PX and looked just in the launch and capture neighborhood. And I'm going to show you side by side. I've used this before. Some people might have seen this before, but up here we've got the high power IR drop map and the low power IR drop map. And then down here, I've got the clock pulse overlaid, the launch and capture overlaid with current through the power and ground pins of this device. And so I'll just show you a quick animation. You can see that without some kind of mitigation, whatever it is, whether it was ATPG or some kind of hardware mitigation, you can get a lot of power draw, and it shows itself differently depending on where exactly all the switching activity is happening. In this case, it's a small design, so it's happening all over the place. It's bad. But with some mitigation on the right-hand side, you can see you can get still good, decent results and low power results if you play the game appropriately. So I'll show that one more time, and then we'll get into some more details about correlation. So, as I mentioned earlier, the old techniques have used flip-flop switching as a proxy for power, and it's not bad, it's not horrible. Some tools even supported combinational gates as well, but you had to do some kind of correlation, because although you could model, this switches a lot, so therefore, I think it has a lot of power draw. This switches a little, so probably maybe it's a little power draw. You only get as good as what you're modeling. And if you don't correlate, you really don't even know how much the tool is really using at a particular slice of time on the tester. So there's some new technology that we're working on, which uses power models to drive ATPG and metrics. So instead of just 1-0 flip-flop switching, we're actually looking at what happens when a flop switch or a clock pulses or combinational logic toggles or memory gets accessed, and how that drives current use of the device. And then also, using if we have the information, using the rail data as well, power rail data to even help us to analyze what's going on there. So the idea is to basically set watts as your threshold, not switching activity, but actual watts, and then you can report in watts. So that's some interesting technology. I think you'll see something pretty soon come out of that, because I think that, again, not only are we seeing kind of more accurate results in terms of what happens inside the device, which is what we predicted, but we're also seeing good pattern count results out of that as well. So it's pretty interesting, interesting stuff. So now I want to get to kind of where the rubber really meets the road, which is, again, last few slides. You can see them on slide 92. I have less than 200 slides, I swear. So the rubber meets the road, we're basically going to drop in sensors, as was mentioned earlier, drop in sensors into the design. We actually recently purchased a company called MEPTEC, which has some of the best sensors in the industry. And we're going to gather data during the manufacturing process, or even out in the field, and mix that in with other data, like what is going on the tester, how things have been set on the tester, what scan speeds are happening, et cetera. So we can do maybe what Dave suggested. For example, we can preempt our observation on one device by moving the current source around or moving temperature around a little bit to help mitigate some of the issues that are about to come up from the pattern that's about to be applied. So this is again, interesting technology to be used to do adaptive test control, or some outlier detection, or some other kinds of interesting things. Again, so the sensors are dropped in, process, voltage, and temperature sensors. We even have a kind of a group of temperature sensors and other monitors as well can be dropped in, along with a management hub to get data in and out. And all this sensor data then can be used to help correlate what's actually going on in the tester with what's being seen inside the chip. And again, these kinds of things can also be used out in the field. to help change things or adjust things from a logic business standpoint or some other kinds of system performance, other kinds of system performance applications like DBFS or those kinds of things. Similarly, we can add in some alerts and other kinds of warnings so that if you've triggered some of these thermal issues inside the design, you can quickly tell something that's listening to you to do something different inside the design, like scale frequency or change voltage or whatever. And if you have the tester still in play here, maybe you can even change the scan frequency again to help you fix yield issues that are happening because of these thermal or voltage droop kinds of issues. Similar to what the AMD paper was talking about that I mentioned earlier. Questions?
Yes, so let me launch the poll, make sure to get you some feedback here. Okay. So I think there is a follow-up question, and it's related to the one I asked before. When you do the repeat fill, is there still not a toggle on the output, or is it the idea is that since you're repeating the pattern, none of the gates from that point should switch? Is that
okay? Yeah. So
the
right
thinking there?
Yeah. So yes, when you shift in, you have the shift in switching activity, and then there's a capture operation which might change some of those bits. Again, we're using clock gating to turn off capturing. So if we've done a good job of filling and that domain has not captured, then we can unload the same data and also shouldn't switch so much. But if there is a capture operation, then yeah, new data is loaded into those flip-flops, and there is switching activity on the way out as well. But all that's calculated in the ATPG algorithms that are used today.
Got it. And so now that you're talking about making the ATPG more power aware, so question is what happens to the development time to develop test vectors and do all the simulation and modeling? I mean, is it a 10% ad? Is it a 50% ad? I mean, it's not free, and that's beyond the paying for the licenses. But I mean, have we just, are we adding a lot of significant test engineering that has to be done to be smarter about this?
Yeah, so I think with every new technology like this, you can see this is obviously new in the domain of mainstreaming this kind of technology. So there'll be this little hump of learning curve on both the EDA, the designer, and the ATE side of the world, and that's happening. But in general, automation is going to flatten that out again. So your return on your investment is almost always going to be there. Similar to when you purchase compression, that costs money because somebody had to develop that. But you get that back on the back end, and hopefully similarly, just as Ken said, you can double your patterns, but recoup 3% of your yield. That's something, right? So I think that's the idea here that we're getting to. That if we can save you some yield, not burn up probe pins, et cetera, that has value. So I think we're trying to leverage that value and leverage the automation to give it to you a little more easily.
Great.
In terms of actual percent, it's as usual, it's design dependent, as is your coverage and your test time and your blah, blah, blah.
Ira, do we have time for a quick question from me?
Sure, yes.
Don't mean to interrupt. Adam, I'm stuck on that picture of a die where you had two identical circuits in the Northeast and the Southwest, and they showed very different thermal profiles. What do you attribute that to? I didn't catch if you said it. Is that a different power voltage levels? different manufacturing. I mean, that could be a nearest neighbor opportunity.
You're talking about this?
Yes.
Yeah. So this is your supply is in the corner here. And so, yeah, there's a distance.
So if the supply's in the corner, wouldn't the one up in that corner be hotter because it has more voltage it's got to manage?
No, I'm showing IR drop, not temperature.
Okay, thank you. My mistake.
No worries.
Okay. Oh, and one last question. In a SoC core-based SoC, what should be done with the cores which are not tested that you'll test later? You're delaying the test. Should they be left to toggle at random, or should they be forced to some state to minimize the current or the power? Sorry.
Yeah, so definitely a quiescent state is generally just fine. You don't want to have a quiescent and contentious state. So you don't want to leave two buses on at the same time, but no clocking. That would be bad. But you know, to the opposite value. But yeah, no, quiescent I think is good enough. That's why I said that for wrap designs, the tools can automatically drop in clock gating so that when you turn off a design from a DFT standpoint, it can actually turn off all the clocks inside the design to keep it quiet while everything else is clocking and pulsing.
Right. Great. Well, I thank you, Adam. A great presentation. So I thank you, and want to once again thank our sponsors who made this event not only possible, but made it free for everybody to attend: Advantest, Amcor, Indium, Form Factor, and Nidec SVTCL. And Advantest, once again, is a global leader in the ATE industry with nanotechnology products supporting leading edge with a diverse workforce and eco-friendly policies. Amcor is driven in the areas of technology, quality, and service in terms of advanced packaging, high quality execution, and a complete array of services from design and test through drop ship with a manufacturing footprint throughout the world. And Indium, with premier assembly materials designer and manufacturer of thermal interface materials, solders, paste fluxes, and materials and compounds. So when you have an opportunity, please thank all of our sponsors and encourage them to help drive future events, but we're very thankful for their support of Too Hot to Test. And I will wish everybody a good rest of your day. Thank you for joining us.